Hello everyone, this is lesson 1.4. Okay, so we just talked about triangles. This lesson is going to focus on quadrilaterals. And also we're going to look at circles, okay, and kind of some of their properties to keep in mind. So if you add another side to a triangle, any triangle, you're going to end up with four sides. And any four-sided figure, those are known as quadrilaterals, okay, so quad being four. And what I want to go over with is five specific cases of quadrilaterals. You've probably seen a lot of these. This would be a good reference slide if you're trying to remember formulas for perimeter and area. In our next lesson, we're going to talk about taking some of these shapes and doing volume calculations as well. So the first two I want to talk about are a parallelogram and a rhombus. Okay, so they've got similar shapes. A parallelogram has opposite sides are parallel. And in doing so, they're also equal in length, right? Remember, regardless of where we are on either of these lines, the distance from that line to this corresponding line in the parallelogram is always going to be the same, and that's because they're parallel. The key difference between a parallelogram and a rhombus is a parallelogram, opposite sides are equal in length, okay? But adjacent sides are not necessarily, okay? A rhombus is if all sides are equal in length, okay? So the way I like to remember these is if you were to take the next two shapes, a square and a rectangle, if you were to tilt the square a little bit to the right or push it, similarly, if you were to tilt a rectangle a little bit to the right, you'd end up with a parallelogram and a rhombus, okay? So that's kind of how I envision those when I think of those shapes. Okay, so basically I've listed the formulas here for all of these. It's important that you understand these formulas and just kind of how they're derived. All right, so for parallelogram and a rhombus, the perimeter is rather straightforward. For a parallelogram, it's A plus B plus B. Or in short form, it's 2 multiplied by A plus B. Okay, so in other words, adding up two sides and doubling it. The area is simply B, or in other words, this base dimension multiplied by the height. Okay, remember the height being in just like an altitude was in a triangle at 90 degrees to that base or B line. Rhombus is very similar. Okay, perimeter is just 4 times S, right? Because it's the same side, S plus S plus S plus S. And the area is simply S, okay, multiplied by, again, the height. Remember, the height being taken at 90 degrees from that bottom line or bottom piece of the rhombus, okay? For a square, square and rectangle, again, a square, all four sides are equal. All angles are at 90 degrees, therefore. Perimeter is the exact same as a rhombus, 4 multiplied by S, S being the length of one side, and the area being S squared. In other words, S multiplied by S, okay? A rectangle, the only difference, opposite sides are equal, just like a parallelogram, okay? And just like a square, it has 4 right angles. So your perimeter, similar to how we did a parallelogram, is the length plus the width, and that's multiplied by 2, right? Because there's 2 lengths and there's 2 widths. The area is simply the product of the length and the width, so L times W. The last shape is a trapezoid, okay? So the top and the bottom sides, B1 and B2, are parallel, but there's no requirements for angles or for these other two sides, okay? They do not have to be at a certain angle. They do not have to be certain lengths with respect to each other, okay? Perimeter is simply just the 4 of these added together, A plus B1 plus B2 plus C. And again, the area is actually a little bit different here. Okay, so it's 1/2 times the height. Again, the height measured at a 90-degree angle to, in this case, what I'm labeling as B2, that line. And it's multiplied by the sum of B1 and B2. Okay, so it's basically taking half, and you add those together and multiplying it by the height. So it's kind of, I like to consider it a cross between the area of a triangle and the area of a square or a rectangle. Okay. So using all of these, my first example is I want to calculate the perimeter and the area for each of these figures. Okay. So let's start with a parallelogram. Okay. Our dimension A is 2.2 centimeters, dimension B is 6 centimeters, and our height is 1.75. Okay, so remember our perimeter is simply 2 times A plus B. In this case, it's 2 times 2.2 plus 6. And if you do that, you get 16.4 centimeters. Okay, I'll actually move that down so we have more space for the other one. Okay, the area is simply the base, or we're calling it B here, multiplied by the height. Okay, in this case, 6 multiplied by 1.75. Again, I'm not showing you the units here, but if this will come out to centimeters squared, and the reason for that is you'd have 6 centimeters times 1.75 centimeters. So 6 times 1.75 is 10.5. And then you have centimeters multiplied by centimeters, which gives you centimeters squared. Okay, that's the case when you look at every one of these calculations. Okay, so it's something that's important when you're starting to look at unit conversions. Okay, all of these examples are in centimeters, but if you had items in different units, you have to know how to convert them. Okay. For the rhombus, okay, your perimeter is equal to 4 times s, right, since all sides are the same. So your perimeter here is equal to 4.2 times 4, okay, and that gives you 16.8 centimeters. Your area is simply s times h, just like the parallelogram, okay. In this case, the area is equal to 4.2 times 3.9. And that gives you 16.38 centimeters squared. Okay, again, remember I didn't show those units, but it is in centimeters squared for the same reason you saw in the first example. In number C, okay, your perimeter is again 4 times s, which is 3.1 times 4. I did those backwards, but you can put them in any order you'd like. And that gives you 12.4 centimeters. Your area is simply s times s, or the way I wrote it, s squared. Okay, either way you want to visualize that is fine with me. So your area is equal to 3.1 squared, which is equal to 9.61 centimeters squared. Okay, doing these basic area calculations, you'll see that these are examples of, a perfectly shaped figure. But you can use a lot of these when you're looking at, let's say, the front of a house. Okay, and it's got different shapes. It might have a peak on the roof, which could be resembled as a triangle. The bottom piece of the house could be represented as a square or rectangle. Okay, so we'll see in our next example how we can add some of these together. The next one is a rectangle. Okay, so the perimeter is 2 multiplied by the length plus the width, right? Because there's 2 lengths and 2 widths. So in this case, it's 2 times 6.1 plus 2.3. And that's equal to 16.8 centimeters. Our area is equal to L times W, or length times width, which in this case is 6.1 times 2.3. And that gives you 14 centimeters squared. Our last example, the one that's got a few more steps, okay? Our perimeter is simply A plus B1 plus B2 plus C. Okay, just adding all of these sides together. So our perimeter is equal to 2.5 plus 1.5 plus 4.5 plus 2.1. And if you add those up, you get 10.6 centimeters. Our area is 1/2 of the height times B1 plus B2. In other words, the two parallel sides in the trapezoid. So that's equal to 1/2 times the height, 1.75, times B1, 1.5, plus B2, 4.5. Okay, so if you calculate that out, and I'll have to write the answer up here, running out of space, the area is 5.25 centimeters squared. Okay, so this is just our basic perimeter and area calculations. In the next example, we'll see how to apply them a little bit further. So a house has a trapezoidal front-facing side with dimensions shown below. Excluding the area of the door, how much siding in meters squared is required to cover the entire side if the walls are perpendicular to the ground? Okay, so you can see they noted that with a 90-degree angle here. Now you can consider this a trapezoid because it has the two sides here, and these sides are both vertical, meaning parallel. So you can calculate it that way and calculate the total area and then subtract this little rectangular piece for the door. Or you can do it another way, and you can draw an imaginary line here, and this would be at 90 degrees, right? Since this is also at 90 degrees. Remember when we talked about angles? And you could calculate this as a triangle plus a rectangle minus this other rectangle. Either way you do it, you'll get the same answer. So I'm actually going to show you both ways to do it, okay? And we will see how the answers differ, if they do at all. They shouldn't, but. So if we treat it as a trapezoid, okay, we have our total area is going to be equal to the area, and I'm going to write T for trapezoid, minus the area of what I'm going to call the door, right? So it has a door that's 200 centimeters by 50 centimeters. So if we do it this way, our area is equal to 1/2 times our height times B1 plus B2. We'll get into what those are in a second. Minus the area of the door. In this case, it's length times width, or we could just write it out as 200 times 50. Okay? I'm not showing the units because if you notice, all these units will already be shown in centimeters. Okay? So now if we're looking at this as a trapezoid, remember B1 and B2 are the two parallel sides. Well, these two sides are the two parallel sides, right? So those are B1 and B2. And since this is at a 90 degree, remember when we had a basic trapezoid, the one you saw in the last example, your height had to be at a 90 degree angle to that bottom line, right? And we can see here that that in fact is the case. So that means our area is equal to 1/2 times our height. In this case, our height is 1200 centimeters times B1 plus B2, which is 600 plus 400. And that's minus 200 times 50, which is 10,000. Okay, so if we calculate the first number out, okay, we get our area is equal to 600,000 minus 10,000, which is 590,000 centimeters squared. Now keep in mind, the question asked for it in meters squared. Okay, so to convert that, we have 590,000 centimeters squared. Remember, going back to our ratios and proportions. For 1 meter, okay, there's 100 centimeters, right? So in other words, if we wanted a meter squared, that's the same as writing 100 centimeters squared, right? Divided by 1 meter squared. Okay, so those are two equivalent things. 100 centimeters is equivalent to 1 meter. That's why we can write that as a proportion. It's not going to change our number here, right? It's not going to change the value. The final number will look different, okay? But it doesn't affect it, it's just changing units, okay? So one thing I did note here that I will have to change is we actually have that backwards. Okay, if anybody might have noticed that. Remember, we want to just have meters squared, not centimeters squared. So we have to cancel out the centimeters squared. So if we want to convert it to meters squared, 1 meter squared, again, is equal to 100 centimeters squared. So what's going to happen is the centimeters squareds are going to cancel and we're going to be meters squared. Okay, so remember, I didn't actually show you that example while recording this to show you how to do it backwards, but I'm showing you, you have to make sure your units are correct when you're doing a conversion, right? Because 590,000 centimeters squared is a much smaller amount than 590,000 meters squared, right? So you have to make sure you convert it correctly. So if you multiply this out, it's equal to 590,000 times 1 divided by 100 squared, okay, which is 10,000. And if you convert that, you get 59 meters squared. Okay? You could do the conversion at the end, or you could have converted each one of these to meters. So this could have been converted to 6 meters. This could have been converted to 12 meters, 4 meters, 0.5 meters, and 2 meters. And the way I did that was I just took 600 centimeters, let's say I do the first one, times, for 1 meter, there's 100 centimeters. So in other words, you end up dividing by 100. So the centimeters cancel, and you're left with 600 times 1 is 600, divided by 100, or in other words, 6 meters. Okay? So that was the way to calculate this if you assumed that it was a trapezoid. But alternatively, like I said, you could assume we have a triangle here, a rectangle, and another rectangle for the door. So our total area would be the area of the triangle plus the area of the rectangle minus the area of the door. And because I've showed you these converted to meters, we'll leave them as meters and you'll see how the answer is actually an easier number to deal with. So our area is equal to 1/2 for the triangle times the base. In this case, the base is the same as this dimension, right? Because it's just right here. So 12 meters times the height, okay? So the height is this portion here. And that portion you can calculate by saying, okay, so my height up to here is 4 meters, but the total height is 6 meters. So that means that height must be 6 meters minus 4 meters. Okay? Next, we have the area of the rectangle. So the area of the rectangle is simply length times width, or 12 times 4. Then we're going to subtract off the door, which was 2 meters times 0.5 meters. Okay? So if we do this, we get the area of the triangle. 1/2 times 12 is 6, times 6 minus 4, which is 2, gives you 12. Plus 12 times 4 is 48, minus 2 times 0.5, which is 1. And if you add that up, you get 59 meters squared. Remember, we get the same answer and we started in meters. So these numbers were a little bit easier to deal with because we converted it at the start. Again, you can approach these questions multiple ways. Okay, so on a test, if you approached it either of those ways, that's fine. If you approached it by converting all of the dimensions first to meters, that's fine. If you kept it as centimeters, that's also fine. Okay, whatever thought process makes it the easiest for you to calculate, that is what I encourage you to use. Okay, and if you do have questions on doing each of these different types, you're more than welcome just to send me an email and I'd be happy to assist. So that was our intro on quadrilaterals. Okay, I just wanted to show you perimeter and area for basic shapes. The rest of this lesson, I'm going to focus on circles. Okay, and a circle is a closed curve. Okay, and all the points are the same distance away from the fixed point. In other words, the center of the circle. So you have this piece here that's the center, and every single point on this circle all the way around is the same distance away. Okay? So some important terms to know. That distance I just talked about between the center and the outside is known as the radius. Okay, that is shown as r. And you'll see it as r exclusively. Diameter is simply the total width of the circle, which is equivalent to 2 times the radius, right? Because no matter where you are, that distance is always going to be the same. It's always going to be equal to the radius. Okay, so the diameter is simply 2 times the radius. Now, those are the basic terms. We're going to see how important those are when we do area and perimeter calculations. The other 3 terms are just instances where things can happen in a circle. The first one's known as a chord, and that's a line that touches 2 points on a circle. Now, unless the chord goes right through the center of the circle, it's not going to be the diameter. In effect, it's going to be a smaller number. Okay, so unless it passes through the center of the circle, the chord will never actually be the same measurement. It'll always be less. Right? You're taking just a portion. Right? So this would be the example of a chord. This would be an example of a chord. All of those would have different dimensions depending on where you are in the circle. A secant is a line that just passes through 2 points on a circle. So you draw a circle, okay? You've got a line like that. That line is a secant, okay? Because it only passes through at 2 points. A tangent is the opposite. So a tangent passes at only 1 point on the circle. So in other words, it's a line that just brushes at one period in time, the circle, okay? So you can see it only crosses at one location and it will never cross through it again. And all of those are different lines. You'll kind of see why those are important as we get further on into this lesson. So first of all, for circles, the basic calculations, just like we did for quadrilaterals, the perimeter and the area. Okay, so they rely on either the radius or the diameter. You can do either one. The circumference or the perimeter. So for a circle, perimeter is known exclusively as circumference. Okay, but in effect, what it actually is the perimeter of the circle. It's equal to 2 times pi. Okay, we'll get into pi in a second. Times the radius, or it's simply equal to pi times the diameter, because remember, the diameter is equal to 2 times the radius. So if you substitute this value into here, you'd end up with the first formula. Similarly, area, you can do it either way. If you know the radius, it's pi r squared. Okay, so pi times the radius squared. And if you know the diameter, it's pi times the diameter squared divided by 4. Again, if you substitute the diameter equal to 2r, okay, you would end up with this formula here. Okay, so they're both identical, and it doesn't matter which one you use. Now, the one number in there is known as pi. Okay, so pi is actually an irrational number, okay, which means it goes on forever and ever. There is never an ending to the number of decimal places after it. Okay, so it doesn't have a finite point. Okay, and what pi is it's a ratio of a circle's circumference to its diameter. Okay, so if you were to take this first equation and solve for pi, okay, so C equals pi times d. Now, if you wanted to solve for just pi, you divide both sides by d. So the d on the diameter on the right side cancels, and pi is equal to C divided by d. Remember, that's a ratio. So pi is a measurement of the ratio of any circle's circumference to its diameter. Okay, and like I said, it's an irrational number. There's one of many irrational numbers that we can talk about. But again, it doesn't actually have an end. So most of your calculators have a pi button. Again, it will store it to a certain number of digits to use in your calculations. I highly recommend you use the pi button and not just the abbreviated form like this. 3.14159 is just pi to 5 decimal places. Okay. So let's look at our first example. A steel pipe has an inner diameter, or ID, of 75 millimeters and an outer diameter of 80 millimeters. So calculate 1, the outer perimeter of the pipe, 2, the cross-sectional area of the steel portion of the piping. Okay, so we've got a pipe, plain and simple. The inner diameter is 75. The outer diameter is 80 millimeters. In other words, a 3-inch pipe. Okay, if you wanted to talk in imperial. So our first question is the outer perimeter of the pipe. So that means the perimeter, the outer diameter. Okay, remember, perimeter in this case is the same as circumference. Okay, circumference is specifically as it relates to circles. So for 1, the circumference is equal to simply pi times d. In this case, it's pi times our diameter and the outer diameter, right? Because that's what it's asking for, which is 80 millimeters. And if you calculate that out, you get 251.3 millimeters. Part number 2 is looking for the cross-sectional area of just the steel portion. In other words, this area in between. Okay? In other words, the thickness of the pipe. Okay? So a lot of times they'll have a rating, okay? Especially if you get into pipes that are like copper or larger pipes. When you get into PVC and ABS piping that's large, they'll actually have an SDR rating, and the SDR rating actually is one of the items that will determine thickness. Okay. Depending on where you're specifying piping, you'll see copper piping more and more on the mechanical side. You'll see PVC, ABS with SDR numbers, especially in large pipes, more in the civil side. So to calculate this, your area, I'll change back to red. Your area is equal to the area of the outer diameter minus the area of the inner diameter, right? Because you don't want this area in the green. Okay, you need to subtract that because it's not actually part of the steel portion of the piping. Okay, so to do that, the area of the outer diameter, okay, remember, pi r squared minus pi r squared, that's the inner diameter and the outer, the piping, okay, or pi times the diameter squared divided by 4 minus pi times the diameter squared divided by 4. Again, this is the inner diameter and this is the outer diameter. We'll use diameter since it's provided, but either one of these formulas would give you the correct answer. So our area is equal to pi times our outer diameter, 80 millimeters squared divided by 4, minus pi times 75 millimeters squared divided by 4. Okay, to just get the steel portion. Okay, and if you do that, you end up with 80 squared, in other words, pi times 6400 divided by 4, minus pi times 5625 divided by 4. And if you do that, your area is equal to 608 0.68 millimeters squared. Okay. One thing you'll notice is as the diameter increases, because your area is related to the square, remember when we talked about direct variation, a 3-inch pipe, okay, your diameter squared would be 3 squared or 9. A 4-inch pipe would be 16. Okay, so a 4-inch pipe can carry almost twice the amount of volume of water, of fluid, as a 3-inch pipe. Okay, and that's because of the relationship when it comes to the area of circles. Okay, so let's look at a second example. This will tie together not only the area calculations we've been talking about for circles, but also some of the other concepts, most notably tangents. The cross-section of a large circular pipe sleeve has 7 smaller tubing runs within it. The tubing are all equal in size and tangent to each other in the outer pipe sleeve. What fraction of the pipe sleeve is occupied by tubing? There's a couple important items to note here. First of all, the inner tubing is all equal in size. In other words, the areas and circumferences of each of these tubes, okay, all 7 of them, are all the same. The second item to note is that they're all tangent to each other. In other words, you've pushed all the tubing together and they all touch each other at one point in each location. Okay? So if I put a dot where each of those occurs, just to kind of show you what I mean, all right? So they touch at each of those points. Okay? This is useful in many applications. There's instances where you'll have piping running or a large conduit or sleeve running under a roadway with multiple smaller pipes within it, whether they're water piping, gas piping, or other piping. You can also see them within large buildings, especially if you're doing heating and cooling piping. You might bundle them together with one jacket around it. In this case, this is more of an electrical application, okay, where you might have multiple wires running through one large conduit. Okay, so it kind of applies within all disciplines. So I'm going to start with our formulas. Okay, so first of all, our area formula, pretty straightforward. Area is equal to pi times the radius squared, or pi times the diameter squared divided by 4. Okay, either one of these formulas works. All right, and what we're trying to find is the fraction of the pipe sleeve that's occupied by tubing. Okay, so I'm going to denote the diameter dl for the large pipe and ds for the small tubing. Okay, so what we want to find is the area of all the tubing divided by the area of the pipe. Okay, that's the fraction that we're trying to find. Remember, when we talk about a fraction, you're always talking usually about something divided by another, or in other instances, if you've already kind of looked at the solution, you'll see it as a percentage in some instances as well. Okay, so I'm just going to write that formula, and then I'm going to describe a few things within this image. Okay, so remember, they were all tangent. So what that meant was, here you can see is the diameter of the small tube. Again, the diameter of the small tube. And again, diameter of the small tube. That's just going from a line from one starting point to the next, okay, of the large pipe. And what you see here is that is actually, if you added all those up, that's the diameter of the larger pipe sleeve. Okay, that's because they're all only touching at one individual point. In other words, a tangent. Okay, they're not squished together. You haven't deformed these circles in any way. Okay, so what that means is the large diameter, or in other words, dl, is equal to the small diameter added up 3 times, or 3 multiplied by the small diameter. Okay. So what I'm going to do is I'm going to substitute that kind of into our fraction here for area. All right. So if I do that, our area of our tubing is equal to pi times the small diameter squared divided by 4, okay? And that is going to be added up 7 times, right? Because there's 7 tubes in here. So in other words, I can show you that you add them all together. Okay? 7 times, or that's equal to 7 times that area calculation. So pi times the diameter squared, or ds squared, divided by 4. Okay? And that's divided by the area of the pipe. And that's simply, remember, pi times the large diameter, which remember is equal to the small diameter. So 3 times the small diameter squared divided by 4. Okay? So I'm just going to do some simplifying here, and then we're going to kind of see how these fractions can cancel out. So this is equal to 7 times pi, okay, divided by 4, times the small diameter squared. All I've done is I was able to move the pi out here, right, and then divided by 4 out here. That's all I did to make it one fraction. Divided by, all right, your first number is pi, okay, divided by 4, that doesn't change. What you'll notice is there's 2 items here. Actually, I'll do it in a different color. There's 2 items here within that bracket, 3 multiplied by the small diameter squared. So you can simply square both those terms. So 3 squared is 9, so that means this is multiplied by 9. And again, it's multiplied by d times s squared, or the small diameter squared. Okay? Now, what this means is you can start looking at canceling some of these items, and I'll show you why. Remember when you divide fractions, all right? So if you have 1 divided by another, okay, that's the same as flipping the fraction in the denominator and multiplying the 2 together. So in other words, what this means is 7 pi times ds squared divided by 4 multiplied by, all I'm doing is I'm going to flip the denominator. Okay, I'm going to flip that fraction, okay, and then you multiply it together. So in other words, this becomes 4 divided by pi times 9 times ds squared. Okay, in other words, the small diameter squared. So what you'll notice now is you have items in both the numerator and the denominator that are the same. And if you have that, you can cancel those out. So first of all, we see we have a pi in the numerator and a pi in the denominator, which means they cancel to 1. We have a 4 in the numerator and a 4 in the denominator. Again, that cancels out. And you have the small diameter squared, both in the numerator and the denominator. So they also will cancel, okay? Remember, terms can cancel as well, all right? So just because it doesn't have a number defined to it doesn't mean you can't cancel it out. Now, if these terms were different, okay, so we related the large diameter to the small diameter. And we did that because this is the same term, small diameter and small diameter. If we left that as dl squared, we couldn't cancel that out because they're different terms, right? One is the large pipe diameter and one is the small. Okay, so if we cancel all that out, we're only left with 2 numbers, 7 on the numerator and 9 in the denominator. So what this means is 7/9 of that pipe sleeve is occupied by the tubing. Alternatively, you could write this as a decimal, which would give you 0.78, around there. Or you could take that decimal and multiply it by 100% to get a percentage and get 78%. Any of these 3 answers on a test are okay with me. Okay, it's whatever you might visualize better. You might think 7/9 of a pipe sleeve makes sense, or you might think 78% makes most sense. In other words, almost 3/4 or more than 3/4 of that pipe sleeve is filled. Okay, again, any of those answers would be acceptable to me. So our last discussion for circles in this lecture will be on radians. Okay, so radians are measuring the angle in the circle. Okay, so radian, a lot of you will see it on your calculator. Okay, so there's 3 different settings most times: degrees, which is what our standard one is, radians, and gradians. Okay, so what those are mainly used for is when you talk about trigonometry, so sine, cosine, and tangent. Okay, when you start to use those buttons on your calculator, if it's in degrees, then the measure of the angle you would input in there would be degrees, all right? So 45 degrees, 90 degrees, 135 degrees, etc. If it's in radians, you would actually input the number of radians it is, okay? So 1 radian is actually the angle where your arc length is equal to your radius. In other words, if you trace a line along the circle here, okay, and you stop at this point and you measure that, okay, 1 radian means that length that you measured by tracing that spot on the circumference of the circle is equal to the radius. All right, so where is that practical? All right, so radians is kind of a unitless measure. All right, and when we look at a circle, if we're doing it as a measurement of radians, okay, when you start to get into trigonometry, you'll start to see that you can use some of radian measures a lot more. Okay, but in the meantime, if we want to talk about how many radians there are in a circle, okay, remember your circumference is equal to 2 times pi times the radius. Okay, so remember a radian is where that arc length equals the radius. Okay, so what this means is that if you go the entire length of the circle, okay, so the entire circumference, you're going 2 times pi times that radius, or that arc length. Okay, so in other words, if you take 2 times pi, that equals approximately 6.28. And what that means is that would happen 6.28 times, okay, if you keep drawing it, going around this circle. So you can have 6.28 radians in a circle, all right? And if you want to translate that to a term you might be more familiar with, in a circle, there's 360 degrees. So that means that 1 radian is 360 degrees divided by either that 6.28 or 2 pi, okay? So because 2 pi is equal to 6.28. What that means is 1 radian is 57.3 degrees. In other words, a little less than 60 degrees. So if you had 60 degrees, you'd know you'd have 6 equal pieces, okay? In this instance, it's just more than 6 pieces, so the angle is a little bit less, all right? So similarly, all right, remember, radians is for measuring angles, right? So radians becomes important when you start trying to measure the length of arcs, okay? So whether it's the arc of a device swinging or something like that, all right? And you can use this to do the length and the area, okay? Similar to how we did circumference and area, using similar formulas, but instead we have radians. So the length of your arc, okay, we're calling it S, is equal to the radius times this symbol, theta, okay? And theta has to be in radians, okay? So it would be, let's say, 1 radian, 2 radians, 4.5 radians, okay? So it's not going to be in any other unit of measure. And the area, similarly, is 1/2 times the radius squared times, again, theta. And theta is the angle measurement, okay? And it has to be in radians. So we're going to do a few examples where I show this, all right? And just to keep in mind, r is still the radius of the circle, okay? R is universally referred to as that, especially when it comes to circles. In this case, S is known, like I said previously, as the arc length. All right? So let's look at our first example. If you eat a piece of pie that is equal to 2.1 radians of an entire pie, and the pie has a radius of 13 centimeters, what is the length of the pie crust and the area of the pie you consumed? Okay, so basic example, you're probably going to think this is really silly to think of a pie in terms of radians, but it's an easy concept to visualize. All right, so I'm going to just draw a pie. Okay, that's a bad circle, but it's my attempt at a circle. And if you remember, I always like to start, okay, on what I'm referring to as this kind of axis here, which is the positive x-axis, and kind of do a visual as to where I think this would end up. Okay, so it's 2.1 radians, and remember, there's a total of about 6.28 radians in the whole circle. So if you look at this, 2.1 to 6.3, 6.28, it's about 1/3. Okay, so we're going to go, I'm going to draw it to about 1/3. And this is just for visual. So this angle is theta. And this, in both instances, is the radius. Okay, so what we're trying to find is S. Okay, it's a bad S, I'll redraw it. S, which is the arc length, and the area. Okay, so in other words, how much pie you consume. So you ate about 1/3 of a pie. That's what we've kind of determined roughly. And the reason I do that is just so that I have a better idea when I'm going to calculate the remainder of our variables, whether I'm kind of on the right track. So two items we have to calculate. First is the length of the pie crust. So S is equal to R times theta. And the second item I'm going to calculate is the area, which is 1/2 times R squared times theta. Okay? So we know a couple items here. We know our radius is 13 centimeters, and we know our value of theta is 2.1 radians. Okay, and what we'll see, and what I mentioned in our previous slide, is radians is actually kind of a unitless measure. Okay, so it'll cancel out as we're kind of moving through this process, and you don't necessarily have to have radians in the numerator and the denominator. It's one of those kind of rare items that stays unitless. So first, we have R and theta, so we can calculate the length. So S is equal to R, 13 centimeters, times theta, 2.1 radians. Remember, the radians will cancel, and this one will just have an arc length of centimeters. Okay? Again, it's just because it's a unitless measure, so keep that in mind when you're doing your questions. So if you calculate that out, 13 times 2.1, you get 27.3 centimeters. Now the area we can also calculate because we have theta and we have the value for the radius r. So the area is equal to 1/2 times the radius, 13 centimeters squared, times theta, which is 2.1 radians. Again, the radians are going to cancel because area in this case will be in square centimeters. Okay, so keep that in mind as you're doing your calculations. So if you do this, you'd end up with 1/2 times 13 squared, all right, which is actually 169 centimeters squared, times 2.1 radians, just to do one additional step. And you get 177.5 centimeters squared of pi. Okay, again, I used pi as an example just to help visualize in this first one before we look at our second example. So our second example, as a ball bearing rolls along a straight track, it makes 11 revolutions while traveling a distance of 109 millimeters. Find the radius of the bearing. Okay, so it makes 11 revolutions, and we know the total distance it traveled. Okay, so this total distance, all right, is the arc length. All right, so that means that S in this case is equal to 109 millimeters. And what we know is it made 11 revolutions. All right, and one thing to keep in mind is what that means is it's created 11 full revolutions around this circle, okay? Because as it's rolling on this straight track, okay, it's rolling and rolling and rolling and rolling and rolling. So we can figure out how many revolutions that is in terms of radians, right? So for every time you have a complete circle, remember, your total number of radians for one circle was equal to 2 pi, or 6.28 radians. So if you make 11 revolutions, your value for theta should be 2 pi, or 6.28, multiplied by 11 revolutions, right? Because it's rotated, or in other words, it's traveled a distance equal to 11 times the circumference of the ball bearing. So if you calculate that out, you get 69.1 radians. Okay? So what this means is we have S and we have theta. We're trying to find the radius. So remember, our arc length is equal to r times theta. So we have two variables, meaning we can solve for radius if we have radius by itself. So to do that, we can divide both sides by theta. Remember, what you do to one side of the equation, you always have to do to the other. Okay, always. So the thetas cancel on the right side, and we're left with just rearranging. R is equal to S divided by theta. Okay, so if we substitute our values in, S is 109 millimeters, and theta is 69.1 radians. Again, remember, radians is unitless, so it will cancel out in this. And if we calculate this out, we get a radius of 1.58 millimeters. So in other words, your ball bearing is 1.58 millimeters with the distance it traveled and how many revolutions it made. Okay? So that's all I had for this lesson. Okay, remember, make sure to send me an email if you have any questions, or please attend our tutorial session where you can ask questions specifically from lessons, or you can ask questions from the exercises in the textbook. One thing I'm going to tell you again is make sure you do the exercises that I give you specifically here. You're more than welcome to try other exercises, but just some of them build on concepts that maybe we haven't covered yet in this textbook, or your textbook will assume that you have covered it because it's assuming you're going sequentially throughout this book. Okay, so thanks everybody.